Okay, sorry that the third lecture got a little delayed. According to plan, it was to come a little earlier, but anyway, some difficulties came on the way. So by next Monday, I hope the backlog will be settled because we get enough time in between. Okay, so in this lecture, in this third lecture, there are important things to discuss, which has to be understood properly and used throughout the course. So, at the end of the second lecture, we discussed the notations to make kinematic diagrams of mechanisms. And here, in the third lecture, we begin with some such diagrams in the display. So, this is a 4R linkage, sometimes also called 4-bar mechanism. It is a 4-bar chain, 4-link chain, and since one link of the chain, link 1, has been fixed, this is notation, so it is a mechanism. And since this mechanism has only lower pairs, so it can also be called linkage. Okay. So 4-bar mechanism is a very famous term. Now this is very close to that, except that the pair between 4 and 1, this one, pair between links 4 and 1, has been changed to a prismatic pair. However, this is also sometimes referred under the general head of 4-bar mechanism by slight adjustment of the term, and because you don't see the fourth as a bar. Okay, doesn't matter, you did not see the fourth bar here also because one link was grounded, one link was fixed. In any case, so these two mechanisms are very close to each other. Here, the rotary motion of link 2 comes to link 4 as a rotary motion, and here it comes as a sliding motion, or the other way around. Anyone can be taken as input, the other can be taken as output. For that matter, in principle, nothing stops you from taking the output from link 3, which is sometimes called as a floating link. Okay, in the sense that no point of it is fixed. Okay, now little bigger mechanism, this one, and you are going to think of how many links and pairs this has, and for that I'm giving you 1 minute time. Think of this mechanism, count the links and pairs, and make a note on your notebook. Later we will talk about it. Okay, so 1 minute break. Break for me, not for you. Okay, you think up and find out the number of links and pairs. In the later part of the lecture, we will discuss that. Okay, so enough time, you got your numbers. So there are 6 links, that is very clear. One is the fixed link, then 2, 3, 4. Sometimes this is called crank if it is a crank. What is a crank? We will discuss that later in some other lecture. This is sometimes called coupler because it is coupling this side and that side. This is sometimes called follower because if it is following, that is following the motion of the crank. Crank is supposed to be the input. Actually, this is the fifth link, which is an extension with which a slider is attached. And the slider slides in the frame itself, link 1 itself. So it has 6 links. Pairs we will discuss later. Now, this is sometimes, this can be called an 8-bar linkage, or more uncontroversially, if you don't want to use the bar, which is a little old-fashioned term, then you can say 8-link mechanism or 8-link linkage. Okay. Look at this a little carefully. This is link 1, which is fixed. If we have freedom, then most of the time we try to show the frame as link 1. There is no compulsion. Okay. So this is a fixed link 1, and it is binary because it is connected here with one link, here with another link. Okay. Now this link 2 is actually a ternary link. Okay. Here it is making a revolute pair with 1. Here it is making another revolute pair with 4, and in between here it is making a prismatic pair with 3. Okay. Now that prismatic pair is binary because it has one pair with 2 and another with 8, and then continues binaries 8, then 7, and then 6 is again a ternary because it is connected with 1, with 5, and here with 7. Okay. And again, these two are binaries. So you can count the pairs at your leisure, and for this there is no need of any break. Okay. So you nicely count the number of pairs, and before the next lecture, you stay ready with your answer. Okay. Now, here I have given an example of a special mechanism. It has a name, 3RPS. Why RPS? Because this is a revolute pair, okay, between the frame and this slot. Then there is a prismatic pair between the slot and the slider. The extension of the slider goes and makes a spheric pair with this top triangular platform. So that is RPS. And 3 such RPS arrangements hold this platform at the top. As it happens, this has 3 degrees of freedom. Okay. And it is sometimes used to orient a camera. Okay. So controlling this in alpha beta gamma, 3 angles. It is actually in a way a wrist mechanism. Okay. Now we continue, and some of these mechanisms we will see again, either in this lecture or later. Special mechanisms we will not see very often in the course, once in a while. Now, revolute pairs and prismatic pairs have a deep kinship among them. And sometimes there is an impersonation between a prismatic pair and a revolute pair. Okay. So for example, see this mechanism. This is one link. Of course, frame is another link, one link. This is the next link. Then there is a third link here, with which there is a slider. But the slider is not moving on straight surface. For that, it's one side. Actually, this side as well as that side of the slider has been made rounded along circular arcs. Okay, the two sides have been made, two faces have been made circular, and it is moving in a circular slot. Now you see, so far as surface motion is concerned, it is sliding. This circular surface slides over this circular surface. But in effect, this is functionally a revolute joint. Because if you had, rather than putting this, if you had put actually a bar, okay, of length that is equal to the distance from this pivot to the center of these concentric circles, and then at that point, if you had pivoted that bar, that rod, okay, then it would be a normal 4-bar mechanism, okay, with all revolute pairs, and the motion of all important points of all links will be as it is in a 4-hour mechanism. So that is why functionally this is actually a revolute pair. So in the structure of it, in the mechanical fabrication of it, actually a revolute pair is there, but it is impersonating as a prismatic pair. Okay. So the slider block with rounded siding faces moving in the circular slot actually affects a revolute pair. So it has to be seen and it has to be interpreted as such and treated as such. And another thing, look at that. Okay, O2A, B, and O4. Okay, and then after a while you say no, we don't want such a small link here. We want a longer one. Then take O4 down. Then you say that we want still longer. Take another down. So when the O4 point, the fixed pivot was here, perhaps the path along which B could move was this arc. Okay. Now when you shifted O4 to here, it became a wider arc. Okay. Then you shift it further down and it becomes a still wider arc. Like that, continue going. Okay. If you shift this to an indefinitely large distance, then the path of B will become almost flat. And that is actually what you get with a prismatic pair. Okay. So shifting the fixed pivot O4 away continually, in the limit we will get a prismatic pair. And the direction of this BO4 actually will give you the normal to the direction of relative sliding. Okay. And this is something which has to be kept in mind, because later in many actual problem solving exercises, this concept will have its use. I mean, very intimate, significant use. So this is something which you need to understand and keep in mind. Okay. One more interesting point. Sometimes it happens that we have a higher pair mechanism, okay, but we would love to consider part of its analysis in the vein of or in the context of a linkage mechanism, lower pair mechanism, for which the geometrical relationships are very straightforward and cute. Now, a higher pair mechanism cannot be totally described by an equivalent lower pair mechanism, because see this, it has one fixed link. Okay, here is one end, here is another end. Okay, so and this profile is that of one of the moving links, and the other moving link has this funny profile, and motion transfer from one of them to the other takes place through this contact of the two profiles. Okay. Now the problem is that with every little movement of this link and therefore that link, okay, the contact point changes and the geometry keeps on changing of the entire mechanism. Okay, and it will become very difficult to express it as a lower pair mechanism forever. However, at a particular instant, for that instant, so far as velocities, accelerations, motion transmission, force transmission, etc. are concerned, you can instantaneously, for that instant, for that particular configuration, you can represent it as an equivalent lower pair mechanism, equivalent linkage mechanism. Okay. The process to do that is that between the two profiles, you have a common tangent and therefore a common normal, and then this profile has a curvature at this point, a radius of curvature at this point. Okay. Basically, what it means is that a planar curve at any particular point locally can be approximated with a circular arc. Okay. And the radius of that circular arc is the radius of curvature. So, along the common normal, take that radius of curvature, mark this point, center of curvature of link CC2. Similarly, on this side, for this profile, for which the curvature may be different, radius of curvature may be different, because they are not necessarily mirror images of each other, you will have center of curvature of link CC3. Now, entire motion transmission at this instant, at this configuration, will be the same as if between link 2 and 3 there were a revolute pair here. Sorry, between link 2 and 3. And between 3 and, okay, actually I cannot call it 3 anymore, this link, because 3 is this. So if we can imagine link 2 having an outside link connected here, and that outside link connected here to link 3, then the motion transmission will be the same as it happens with the help of the two profiles touching each other. Okay. So this particular 4-link mechanism, 2, 3, 4, and 1, of course, the frame, is the instantaneously equivalent linkage mechanism of the original mechanism. At another instant, at another configuration, it will be another similar construction. Okay. The common normal will be different, common tangent will be different, and radius of curvature also will be different, because another segment of the profile will appear in contact. Okay. But structure of that will be similar. So what we have done? A profile contact, a higher pair, line contact or point contact, has been replaced here by two lower pairs and an extra link in between. Okay. So a higher pair can be conveniently replaced with two lower pairs and a link in between in this manner to get an instantaneously equivalent linkage mechanism. So at the centers of curvature, you get the equivalent positions of the lower pairs, the two lower pairs that you put in order to replace them. And you should make note that this equivalent linkage has validity. This equivalence has validity only at this configuration. At another configuration, there will be another forward linkage which will be valid. Okay, another two lower pairs, another intermediate link, and so on. Now, this is one interesting thing that sometimes gets tubes. And now one of the most important things of this lecture, kinematic inversion of a mechanism. Just look at this mechanism. This you have seen there, the side diagram. Okay. So revolute pair, revolute pair, revolute pair, and prismatic pair. This is a typical engine mechanism. Okay. So this is the crank, rotating which is perhaps the purpose of this engine. Okay. And here is the piston. Okay. So crank, piston, connecting rod, and frame, which is actually the cylinder, and crank pivot here. Okay. Crank pivot. Okay. So now, what are the relative motions between fixed link and each of the other links? Between 1 and 2, it's a pure rotation. Fine, because 1 point is fixed. Between 1.4, it is pure sliding. This way and then that way. This way and that way. Okay. The prismatic pairs will always have limits. Otherwise, they would go all the way to Pluto and beyond. Okay. Revolute pairs do not need limits because after 360 degree, they come back to the original place. They don't go to Pluto. Okay. I mean, not necessarily, unless the size is very large. Okay, so between 1 and 2, it is a rotation. Between 1 and 4, it is a sliding. What about between 1 and 3? As you see, no point of link 3 is really fixed. This point goes on moving around this fixed point in a circle, and this point goes on moving along a line. As a result, this link itself oscillates like this, in which it translates, rotates, does both. Okay, in a little funny way. For each instant, you can find out the motion as a rotation about some point, but then that will keep on changing from one instant to another. Okay, so these are the three kinds of motions that is taking place. Now, from here, what we have done, we have turned this mechanism by 90 degrees. Okay, you see this horizontal thing, link 1 has become vertical. This inclined thing has become this inclined thing. This floating fellow has become this fellow, and this slider has become this. So, and what big thing we have done, link 1 is no more fixed. We have freed link 1. Okay. At the bottom of it, we have put a bucket. We have fixed link 4 now. Okay. Link 4, that is fixed. That is the ground. And then with the ground, that is with link 4, link 3 is connected as usual. Okay. And with link 3, link 2 is connected as usual. Link 2, link 1 is connected like earlier, except that 1 is no more fixed. Now this has become a hand pump with a different purpose. You see, you put the handle, lift it, your bucket goes down, then get the handle back, and bucket full of water comes in, right? So this is one mechanism for one purpose. Of course, on the way, link 3 has become a little shorter, but that is a matter of detail. Structurally, what has happened? We have released link 1, allowed it to move. Okay, now it is the bucket, okay, which is coming up, going down, coming up, going down. As you take the handle and go up and down, up and down. Okay. Basically, when you take this up, this goes down, and the other way around. You know how a hand pump operates. So, this is called an inversion of this mechanism. Or alternatively, if hand pump was original, then you would say that this is an inversion of that. So either way you can say. Okay? So by inverting a mechanism, you change the fixed link of the chain. Sometimes you talk of inversion of a mechanism. when you take a mechanism with already one link fixed and then release it, okay, let it move and fix another link and then start doing something else. So you say you have inverted the mechanism. Sometimes you can also say that to begin with we have this kind of kinematic chain, not mechanism. That means no fixing has been already mentioned. Okay, and then you say now I can fix one of the links to get one inversion of the kinematic chain. The correct reference of inversion is to a mechanism by two-step process, freeing the frame, proposing a different frame. But then, in a little corrupted sense, but quite popularly, it is used in this way also. That to begin with, we had a 4-link chain, and now this is its inversion with link 1 fixed. This is its inversion with link 4 fixed. And you can get 2 more inversions by fixing link 2 and fixing link 3. Okay? So this inversion is something like friend. You are my friend, I am your friend, and we are friends. Okay, so like that, inversion word is used. So here it is, you are my friend, I am your friend. In that sense, it is used. Here, we are friends. In that sense, it is used. So either way, it is used. This is the original sense because inversion literally means that. Okay. Now, you do one important task on your own. Why? Because the book covers this in good detail and a lot of nice pictures are there. Okay. And you can draw sketches on your notebook. So study 4-link single loop closed chains, all their inversions. So considering revolute pairs and prismatic pairs as different, how many different such single loop closed chains you can think of? One is 4R, all revolute pairs. In that, technically, no inversion is possible because all that can differ among the links is that their lengths are different. Okay. Otherwise, there is no kinematic structural difference between this link or another link. Okay. However, among the 3R1P mechanisms, there can be 4 kinds, which is fixed. So 2 of them I have shown here. This is 3R1P. So 3 revolute pairs and 1 prismatic pair. Okay. So which one you fix, based on that, it will be decided. So which inversion you are talking about. Then with 2 revolute and 2 prismatic, you can think of RRPP. Interesting inversions are there. Or you can think of RP. So if the 2 revolute pairs all are closed chains. Okay. So here the 2 revolute pairs come successively and 2 prismatic pairs come successively. Here they come alternate. And make note that the other possibilities which you could think of, 1R3P is not possible in a closed chain. Okay, 1R3P is not possible. I mean, either it is not possible or it will be meaningless. Similarly, 4P is not possible or meaningless. Okay, and you will find out how it is. If you can't find out, then raise that issue in the forum or next time in the discussion. Before we close in this lecture, there is another important thing which I want to introduce to you a little earlier than its time, but roughly at good time, because very soon we will need that in the next lecture perhaps. And here is again another mechanism which has come earlier once. I asked you how many links this has. You must have found out that it has 6 links. 1, 2, 3, 4, 5, 6. How many pairs does it have? Okay. You can see 1 between 1 and 2, 2 between 2, 3, and then 3 between 1 and 4, then 1 and 6. Okay. So 1, 2, 3, 4, then between 5 and 6, 5. What about this? Is it a pair among links 3, 4, 5? It is meaningless talk because that cannot be a pair. Okay, pair is a collection of 2, a meeting of 2. Okay, so it is not a pair. So what is it? Is it? It is not one pair, first of all, because pair is constituted by 2 elements. Here we have got 3 elements. So is it 3 pairs? A pair between 3 and 4, a pair between 4 and 5, and a pair between 3 and 5. It will be like an overkill, right? It is an overkill, and nobody considers it as 3 pairs. However, you can have a position that it is actually 2 pairs. Okay. For example, you connect 3 and 4, hold hand like this, and then the third friend comes and hold hand like this. That is good enough. All 3 get connected. Okay. Now, another question will arise, and this will be a practical question when you solve problems. Okay. Or when you try to analyze this mechanism, when you try to do number synthesis. Which is a ternary link? 3, 4, 5. So, whose hand is being held by 2 of the friends? Okay. Now, you can look at this mechanism as this, in which 3 is the ternary. Okay. And this is the link 3. With this dimension, delta, small, very small, extremely small, almost 0. Okay. And you get this in practice. Or you can consider this mechanism as this. Okay. This is actual link in which this dimension, delta, is small, etc. Okay. Or you can look at it like this. Okay. So, how do you look at this mechanism? This way, or this way? So, here the link 3 has been taken as ternary, here 4, here 5. All these 3 perspectives are equally valid, actually. Okay. And you see double pair now. In each of these 3 cases, you see double pair. One pair here, one pair here. Here also. So the double pair you can see, or you can imagine, you can visualize in your mind if you look at it like this. And for that, you will invariably need to consider one of the 3 links as a ternary link. Okay. And now, how many pairs you have got? 1, 2, 3, 4, 5, 6, and the sliding 7 pairs. In each of them, you will get 7 pairs. And the count is consolidated by considering this as a double pair, equivalent to 2 pairs. Like that, in principle, you could have triple pair, quadruple pair. In general, you can talk of multiple pairs. So if at one pin, if there are 5 links connected, then that is actually equivalent to 4 pairs. Okay? Because take one of them as the master and then say it is connecting to this fellow, that fellow, and the other fellow also. Okay? So you can say that. Or any way you can distribute. One is connecting with 2, another is connecting with 2, and you can do all that juggling. All of them will be equally valid like this. Okay? But overall there will be 4 pairs. So here there is a double pair among links 3, 4, 5, which is equivalent to 2 simple pairs. Any of the 3 links here can be treated as a ternary link, and all 3 perspectives are equally valid. To me, this looks more straightforward the way I love to think of it. But if you like to think of it like this or this, I can have no issues with it. Now, why I think this is more lovable? Because here one loop of the mechanism is little 4-link loop and another is 1, 4, 5, 6. There is another 4-link loop, so they get partitioned. Okay. So what it means is that if I think of it like this, and if the linkage is actually like this, then even if this delta is not very small, the analysis becomes no more complicated than just two standalone forward linkages. So that is why I find this lovely and this not so lovely but manageable. Okay. So you try to find out the loop sizes. Of course, here the third loop, 1, 2, 3, 4, 5, 6, 1 is also a loop, but I don't have to analyze it. Okay. If I can analyze it this much separately and this much separately. Okay. So that is why this is easier to think for that purpose. Okay. So I think I'll stop at this point and continue a thorough, in-depth discussion on these freedoms and their dependence on number of links, pairs, and their arrangements, and so on in the next lecture. So I stopped sharing, and the third assignment that we will have with this, you will need to submit on Monday, because this I'll upload on Monday. I mean today itself.